Let's talk about mass spectrometry. We'll introduce mass spectrometry and go over some ion sources. We'll take a brief look at mass spectra, what they look like, the basic components of the mass spectrometer, and then what ion sources do. And then we'll look at some specific ion sources, ESI, APCI, EICI, ICP, and finally ambient ionization. That's a lot of acronyms. We got a lot of alphabet soup going on. So in our previous LC video, we clicked around in the chromatogram and saw the mass spectra below. So if we look at the axes in the mass spectra, we have y-axis is going to represent intensity, and remember the x-axis is going to represent identity. That's the qualitative identification. So in mass spectrometry, the identifying information is the mass to charge ratio. And that's going to be related to the mass of the compound, the fundamental mass of the compound. Now in LCMS, we tend to get intact spectra, but look here, this is for cocaine, which has a mass of 303, and we have a peak at 303, but we also had a bunch of other peaks. Here's scopolamine, which has a mass of 303, and a bunch of other peaks. These are fragmentation spectra. So we're going to get information about the mass of the compound and potentially its fragments if we have a fragmentation spectrum. And this is not mass like grams or kilograms. This is fundamental mass, like atomic mass units, or another way of calling it is Daltons. Now, it is mass to charge ratio, but for most small molecules, most of the time, the charge, the Z, is 1. So M over Z is M, is mass. So let's look at the basic block diagram for a mass spectrometer. Mass spectrometers can only look at ions. They can only look at ions, and the ions have to be gases. They have to be spaced out. They have to be far apart from each other. So before the sample really gets into the instrument, you have to put it through what's called an ion source. And the point of the ion source is going to be convert your sample into a gas and into an ion, or what we call a gas phase ion. After that, it passes into the heart of the instrument, which is called the mass analyzer. That separates all the different mass to charge ions. And then finally the detector, which converts the ions into some kind of readable electrical signal. Again, like we talked about previously, that's probably going to be voltage, current, or frequency. Now, you have to have vacuum in a mass spectrometer. You have to keep the ions separated. Some ion sources have to be in the vacuum, some do not. That's what you're seeing represented in the top and bottom diagram. But all mass analyzers and detectors have to be kept under vacuum. A lot of the time, in fact, probably most of the time, you're going to end up running chromatography before the mass spectrometer. And we've already seen this. We've seen LCMS and GCMS. If it's a messy sample, if it's a really messy sample, you're going to have to do some sample prep ahead of time. A lot of times a liquid extraction. And then the chromatography is going to help you separate things further. And then each peak is going to go into the mass spectrometer. So it's really common to couple chromatography with mass spectrometry like GCMS or LCMS. Now that we've looked at some block diagrams, let's go real instrument. So this is the ion source for the instrument. This is where the sample comes in. In this case, it has to come in as a gas. It's converted to ions. And then this part is the mass analyzer. It's kind of a cool horseshoe-shaped mass analyzer. So the ions fly through the mass analyzer and get sorted by mass to charge. And then finally, they impact on this golden part here at the end. That is the detector. Now, we keep the instrument in vacuum because we do not want boom. We don't want that. We don't want these ions that we create to collide with each other. Ions are pretty unstable. They're going to respond beautifully to our electrical magnetic fields, but they're pretty unstable, and if they, boom, collide with each other, then we get reactions. A lot of times we neutralize our ions, but we don't want that to happen. So in this simulation, we can see that at higher pressure, we have all this gas in there colliding with each other all the time, and there's a really high likelihood of reactions. But if we suck that gas out, if we make a vacuum, there we go, a lot fewer collisions, a lot less likely that our ions are going to hit each other, react with each other, neutralize our ions, or just have reactions we don't want. So let's look at this in more concrete terms. We'll look at this in terms of pressure and what's called mean free path. Now I've made some assumptions here just to get an approximate mean free path. Mean free path is if you have a gas molecule at a certain pressure, how far does that gas molecule travel before it collides with another gas molecule? So it collides with one gas molecule on average, the mean, how long is it going to travel before it collides with another one? You can see at ambient or atmospheric pressure, 760 torr, it's going to have a mean free path of 130 nanometers. So every 130 nanometers or so, it's going to crash into something. It's going to crash into a lot of gas in atmosphere. There's a lot of gas running around in atmosphere. When you get to 1 torr, that's about the intermediate vacuum region of a mass spectrometer. That's in the region of what you guys were in when you had those vacuum desiccators in analytical. Now we're at 100 microns, a little bit longer, but still our gases are going to run into each other a lot. When you get down to 10 to the minus 3 or 100 millimeters, by the time you get to where most mass analyzers are in mass spectrometry, 10 to the minus 5th and 10 to the minus 7 torr, it's much less likely that these things are going to have collisions with each other. On average, an ion is going to have travel between 10 meters and 10 kilometers before it crashes into another gas molecule. By the time you get into the vacuums of deep space, and there's a lot of different pressures in space, then you are talking about, on average, a molecule is going to hit a gas atom is going to hit another gas atom or molecule every 1,000,000 kilometers. You know, roughly every 600,000 miles or so of traveling, it's going to hit gas. There's just not much there. So in the heart of the mass spectrometer and mass analyzer, we tend to operate at 10 to the minus 5th to 10 to the minus 7 torr. And it's a little bit of work to get there. You actually have to use 2 vacuum pumps working together to get down to those kinds of pressures. Let's take a look at what we're talking about. So we are taking a tour through the lab here, but we're going to pay attention to those big noisemakers in the lab, those vacuum pumps. So if we go over to our GCMS over here and we look down on the floor, there we go. That is a rotary vane. That's a mechanical pump, also called a roughing pump. There's a vacuum tube connected from that to the mass spectrometer. The other pump for the instrument is inside the instrument. If we go over to this GCMS, which we'll use a lot in toxicology, again, we have a big noisy mechanical vacuum pump on the floor, vacuum hose going into the mass spectrometer, which also has a second vacuum pump inside of it. If we whip around here and take a look at the LCMS, the mass spectrometer on the LCMS, we have a big, this guy has an atmospheric pressure interface. So we have a big old pump that goes on this guy. Our other mass spectrometer actually has 2 of these big giant pumps. So big noisy pumps everywhere outside, and each of these mass spectrometers has a second pump inside. Let's take a brief look at how those pumps work. So you have to have a pump that is able to work at atmosphere and pull some of the gas out of the chamber, pull some of the gas out of the instrument. This is called a rotary vane pump. Any pump that gets you down to those first initial pressures, we're just going to call a roughing pump. And it's just sort of a spinning turbine that seals and pulls gas out of the chamber and then blows it out into the room through that diaphragm there. This one has is a dual rotary vane pump, but you just have to have these. The role of the pump is called a roughing pump. So it gets you from about 1 atmosphere, or it gets you from about 760 torr down to maybe 1 or 1 or so torr, but it depends on the dimensions of the instrument and things. But this is going to get you going with the vacuum. You need another stronger pump called usually a turbomolecular pump. This is a turbomolecular pump you see here to get you down to lower vacuums. So it has that spinning kind of vane on top, and then there's that big base. You see that it's shoved up into the instrument chamber, and it's just sucking gas out of the chamber. This is called a turbomolecular pump. It doesn't have to be a rotary vane pump and a turbomolecular pump, but that's the most common combination. So the turbomolecular pump really is a lot like a jet engine. That's, instead of we're using it to blow, it's blowing out, but we're pointing the end that sucks in at the chamber, and then it's blowing that gas out in the room. It spins incredibly fast. It actually can't operate at atmospheric pressure. If you fire these up at atmospheric pressure, they heat up and they get destroyed, and they're very, very expensive. So you have to have another pump to back them up. And these guys really are just like taking a jet engine and pointing the part that sucks in at the chamber. And this reminds me of the cliche in action movies where, oops, the bad guy gets sucked into the jet engine.
No kicks!
So we looked over the basics of mass spectra. We've talked about the components of mass spectrometers. Let's move on to looking at generally about ion sources and then some specific ion sources. We'll start with electrospray, ESI, that is, and APCI. So the job of the ion source is to take whatever you give it. Some of them work with some states of matter better than others, or they don't work at all. You put your stuff in the ion source, and it has to come out as a gas phase ion, and then you transport that into the mass analyzer where it's sorted and then the detector. There are a lot of different ways to organize ion sources, but I think probably the most significant one is going to be what's called hardness, or what kind of ions these ion sources make. There are some really called soft ion sources that don't disturb the molecule much, and the mass that you get is very representative of the intact molecule. There are others that are very, very hard ion sources. They put a lot of energy into the ion source. Some of these ICP and thermal ionization put in so much energy that they strip away all chemical bonds, and you're just left with ionized atoms. Regardless of what you put in, you get ionized atoms, so we call these atomic ions. So those are the very hardest of ion sources. And then the softest of ion sources take a molecule intact and gently put it into the gas phase. And then there are ion sources in the middle that make some molecular ion or protonated molecule, some ion peak that's representative of the intact molecule, but they also generate fragments. They put in enough energy that they make some intact peaks, but they also make peaks for the smashed up and partially destroyed fragmented molecule. So that's probably the most important characteristic of an ion source is what kind of ions does it make? There are some other ways to group ion sources, like does it have to be in vacuum or can it be in atmosphere? Do you have to do chromatography with it, or can you get away with not doing chromatography? And then what state can the sample be in? Does it have to be a solid? Does it have to be in a solution? Does it have to be a gas? Or can it be any one of those things? So there are certainly other considerations when it comes to ion sources, but the most important one is what kinds of ions does it make? So here's one of our mass spectrometers. This is an ion trap I use in my research. And this is an electrospray source on it. It's actually a modified source. We modified it for research. But you can just pull the ion source off the instrument. That doesn't need vacuum, so there's no vacuum chamber, so you can just pull it off. That was the electrospray ionization source. Truthfully, it was modified a little bit. Now, we're going to zoom in here. So that's the ion source that makes the ions, and that hole, there's a little hole in that capillary right there. That is the inlet. That's the inlet to the mass analyzer where the ions get pulled in. If we take a look at the electrospray source here, we can kind of make out there's this needle on the tip, and that's going to be really, really important. There's this needle on the tip, and that shape sort of goes, that needle right there at the tip. When we swivel this guy around, we'll see that there are connections for gas, to get gases in if we need them. There's connection to bring the voltage in and to bring the liquid in. So here is the LCMS that you guys will be using a lot for forensic toxicology. You can see there's a capillary tubing. That should look familiar from GC. That brings in little bits of liquid into the source. And then there's the voltage in the gas that can come in. And we look down on top of this guy, and the angle's a little bit different, but we have that needle. That's the electrospray needle coming in. And then that tip at the very front of the instrument, that's going to be the inlet that samples the ions. Let's take a closer look at this one. So there is the electrospray needle tip, and it is orthogonal. It's at a right angle to the inlet part of the mass spectrometer there. Here's yet another electrospray source, but this is an action. You can faintly see that spray coming out. So let's talk about what spray is. So if we look at this cool slow motion of a spray bottle, there are those tiny, there's no voltage or anything being applied here, but it's generating what are called aerosols. These are not gases. These are tiny particles of liquid, but they're so small that they float in the air, and they're also small, so they dry up really, really, really fast. Now, another gross example of aerosols, but a really important one now here with coronavirus, and one of the reasons that it propagates so well through sneezes is that when you sneeze, achoo, you generate bunches and bunches of aerosols, and these aerosols are really small particles with molecules encapsulated in solvents and liquids, and they float through the air, but because they're so small, they also can dry up really, really quickly. And we're going to rely on this for the electrospray mechanism. We're going to generate aerosols, but we're also going to do it under high voltage. So we have that needle. We're going to apply very high voltage, very high electric field, so there's a bunch of charge there. And then we're going to spray aerosols with this bunches of charge, this 5 kilovolts, very high electric field. And that's going to generate charged particles. We're going to have this jet of stuff coming out. The droplets are going to get smaller and smaller and dry up more and more and more as they pass through the air because they're so small. So they're charged. They've got a bunch of charge in these droplets, and they're drying up more and more and more. And this is a bit of a trick because our molecules are in those droplets. And as these droplets, the solvent dries up, it's called desolvation. The molecules are closer and closer to being left alone. And eventually, when all the solvent has dried up, and the molecule is left alone and it has charge on it, well, if you're a molecule and you're all alone, you're a gas. And if you have charge, you're a gas phase ion. So here's a cool little animation. We have these solvated ions with charge on them, and they dry up into smaller and smaller particles, and eventually you just have one molecule and a little droplet, and then when that dries up, you are left with a gas phase ion. This is a very gentle ionization mechanism. Now it relies on the charge, the plus, comes from H+. It's protonation. So that's why when we look at LCMS here, and LCMS is usually going to be done with electrospray, or its kind of close cousin APCI, which we'll look at in just a second. But you can see cocaine has a mass of 303. We get a peak at 304, and that's because it is protonated. And we get an intact peak at 304 because it's a nice gentle ionization. Here is yet another mass spectrometer with an electrospray source, but I'm showing you this guy. We'll open it up, and I'm showing you this guy because I want to show you a kind of a cousin of electrospray called APCI. And the physics are different, but usually if you have an electrospray source, you're going to have an APCI support source. It's an accessory that comes with the instrument, and it can be, we're doing electrospray. There's the needle, and there's the inlet to the mass spectrometer. But all we have to do is flip this lever up so that we have this needle pointing between the spray and the inlet. So there we go. We flip that needle up. Now that needle is kind of pointing there between the spray and the inlet. And if we change the voltage, we change a little bit in the software, we're now doing atmospheric pressure chemical ionization, or APCI. So if you have electrospray, you usually have an APCI accessory. It's a nice, simple transition, and almost all LCMS instruments have both sources attached to them. Let's talk about how this works. So to do that, let's play with this guy that we played with in class. This is a point. It's not as sharp as it used to be, where we're applying bunches and bunches of voltage in atmospheric air. And we get what's called a corona discharge. It is ionizing the air at the tip of that needle with corona discharge. That's what we're going to do in APCI. Instead of applying the voltage to the needle where the sample is coming out, to the sample spray so that we produce charged droplets, we're not going to produce charged droplets. We're just going to nebulize. We're just going to spray aerosols. Now, usually there's a heater there, so we spray the aerosols and usually heat them up a little bit. But then that needle is right there in the way of the aerosols, and it has a corona discharge. So it has a bunch of ions. It's ionizing the air, and a lot of times what you end up with when you ionize air, ultimately one of the more stable things that can form in air, or the most stable thing can form in there, is hydronium, H3O+, can form from the water in the air. So if you make kind of a cloud of H3O+, your stuff runs into that, the H3O+ can transfer its proton to your stuff, and you end up with a protonated molecule. Now, you can also end up with oxygen radicals and nitrogen radicals and some other things that are a little bit more aggressive. Those have some more energy. So you do end up with a little bit more fragmentation in APCI. It's a little bit higher energy than electrospray, but it also lets you ionize some things you would normally see. So here's the general cascade of reactions, a typical cascade of reactions you're going to see in APCI. You generate these free electrons in the corona discharge. They can ionize nitrogen. They can also ionize oxygen, but these things crash into water and through a cascade of reactions ultimately generate H3O+, which is relatively stable. But still, H3O+ is really good at it's a really good acid. It's good at giving away its H+. So when your molecule runs into it, you wind up with your M plus H+, your protonated molecule. You can also look at negative ions from all these sources, from ESI and all these other ones. They'll produce negative ions. In the case of APCI, the mechanism is usually in negative mode. The OH minus that you generate strips an H plus off of your molecule. So as you might guess, in both electrospray and APCI, and really all these ion sources, you're more likely to get positive ions for things that are okay with being protonated. Definitely amines. Amines ionize very nicely. And you're more likely to get negative ions from things that deprotonate nicely. So certainly carboxylic acids or phenols, even some alcohols and things. The protonation and deprotonation in the gas phase in an ion source is pretty aggressive. So you can protonate some things that you would be surprised would take a proton, and you can deprotonate things that you would be surprised would lose a proton. Okay, so we went over some basics of mass spectra and the components of the instruments and the ion sources. Now we've looked at ESI and APCI. Let's move on to, those work well with LC. Let's move on to some things that work well with gases, but don't work well with liquids, EI and CI. So these work well with gases, and they're on our GCMS, while EI is. Let's open up our GCMS there, and you can see there's a big EI right there for electron ionization. That is our EI source. So let's pull this guy out. So it's sealed up because EI and CI have to be done under vacuum. They have to be in vacuum. So again, EI is electron ionization. An old school term for it is electron impact, and you may hear some people refer to it. That's kind of an antiquated term. It's not an accurate description of what happens. So let's pull this source out and kind of take a look at it, and we'll take a closer look at the components of this chamber later. So this is our EI source on the GCMS. And this is probably the most common ion source in all of forensics, next to electrospray for LCMS, which they use in toxicology. So we pull the source out, so we kind of look down the barrel here. You can see the beginning of some ion optics. It's really hard to see, but if you look on the right, you can actually see the column poking into the ion source. So we have the GC column feeding directly into the ion source. So it feeds the gas in, it gets ionized in the source. Let's take a closer look at this chamber here. So at the heart of it, we have this filament. We have a filament, and this is really just kind of a fancy old school light bulb filament, but its point is it generates an electron beam. Okay, now for the rest of the chamber, we're going to have a repeller, which when the ions form, it pushes them out of the outlet on the other side of the mass spectrometer. And on the one side, we have the hole where the column just barely leaks in there, so gas can leak in. So let's take a look at what's happening here. So for this demonstration, we'll say the repeller's on top. That'll be the filament. See the electron beam, the outlet, and then we'll have this guy kind of drift into the chamber. So the gas drifts into the chamber, gets into the ion beam, becomes a positive ion, and the repeller is held at a high positive charge, and that pushes it out of the chamber and into the mass spectrometer. Electron beams are a pretty simple way to put energy into molecules, and you tend to, at least initially, get an ionization event where the molecule absorbs the energy of the electron beam. It absorbs an electron, essentially. That results in excitation, which ejects an electron from the molecule, and then you end up with this radical cation, M dot plus, but that has the same mass as the molecule. And we call that the molecular ion. We call it the molecular ion. Now, that is not always stable. Sometimes you'll ultimately see the molecular ion in the final mass spectrum, but that's usually not stable enough, so it's going to break apart and fragment into pieces. So sometimes the molecular ion shows up in the EI spectrum most of the time, but sometimes it doesn't. Sometimes all you get is fragments. This process is not terribly efficient. Only about 1 in 1,000 molecules that run into the electron beam will be ionized in this way. So we say that it is about 0.1% efficient. The efficiency for electrospray and APCI, in other words, the number of molecules that you pump in compared to the number of ions that actually you come out, varies enormously. For things that like to pick up protons or get rid of protons, the efficiency can be really, really good, like in the tens of percent or closing in on nearly all of them. But for other things, it can be really small. For alkanes, it's almost zero. EI is pretty constant in its ionization efficiency, but still only about 1 in 1,000 things that wander into the electron beam get ionized. That's still plenty. It still can be very, very sensitive and powerful technique. It definitely gets the job done. So let's take a trip down memory lane. I know you guys love to think back about Gen Chem. Periodic table trends and ionization potential or ionization energy. And you said, as you go up the periodic table and to the right, ionization potentials get larger. So helium has a huge one, and those guys at the bottom have a smaller one. So here are some examples of ionization potentials. Potassium is 419 kilojoules per mole. Gold is 890 kilojoules per mole. That corresponds with those periodic trends. I want to point out, in mass spectrometry, we're going to switch energy units. It's just a conversion factor. We're going to use something called the EV, or the electron volt. It's very important you recognize this is not a volt. An electron volt is a unit of energy, A volt is a measure of electrical potential. But electron volts are really nice because a few electron volts tends to be on the order of bond energies or ionization potentials. So in mass spectrometry, we're going to, instead of using joules and things, we're going to use electron volts. So potassium's ionization potential is 4 electron volts. Gold's ionization potential is 9 electron volts. Mercury's ionization potential is 10 electron volts. So in theory, we could put 10 electron volts of energy into mercury and it would ionize. But if we look at this plot, it's telling us as we increase the energy, we increase the number of ions that we actually get. So while 10 is the bare minimum, you can see on that plot at 10, that's when you actually start to get ions. On the y-axis, they're kind of telling you how many ions you get. 10 is the bare minimum. You can get ions at 10, but you don't get many at all. As you increase to 20 electron volts, 30 electron volts, 40 electron volts, at 40 or 50 electron volts, you get so many more ions. You get so many more ions. So generally, we're going to run EI sources at higher energies than we need to just barely ionize them, just because we get so much more signal. We get so much more overall ions. So the energy that almost all EI sources are going to run at is 70 electron volts. That's a magic number. That's one that you want to know. And that's because on average, organic compounds tend to do really well at 70 electron volts. They tend to be able to absorb 70 electron volt electrons quite well, and you get a lot of ions. Now, it's kind of too much energy, so you're going to wind up getting fragments, but still, you're going to get a lot of ions overall. So we were looking at elements and things, but most of the time we're doing organic molecules. So let's look at some bond energies, typical bond energies for organic bonds. And we can see they tend to be on the order of a few electron volts. We got that guy over there in the corner who, with that CH2H single bond, is 1.5 eV. And then that strong triple bond there on acetylene, that's 10 eV. But the bond energies tend to be between 1 and 10 electron volts for organic molecules. Of course, triple bonds are going to be stronger than double bonds, are going to be stronger than single bonds. So this ties into the bond energy work you did in organic, but instead of talking about kilojoules per mole, we're going to talk about electron volts for our bond dissociation energies. So at 70 electron volts, we are putting way too much energy into these, and we're going to get a lot of fragments. So if we look at this, this is benzoic acid with ionized in an EI source with 9 electron volts, 12 electron volts, 15, 20, 30, and 70. And 9 looks great. Look at that. You just get the molecular ion. You don't get a bunch of fragments. But the truth is, that signal, you have to put so much benzoic acid in there just to get a peak for that. The signal is terrible. And as you go up in energy, you start to get more and more fragments, but you also just start to get more and more signal. You start to get more and more ions. At 70 electron volts, that's about optimum for ionization efficiency. That's about optimum for signal that you're going to get. But you do get a bunch of fragments because you break bonds. But the trick is, because we've all agreed to 70 electron volts, that fragmentation can really turn into an advantage for us. It can give us almost a fingerprint for the molecule. It can give us a lot of peaks to compare, and it can be very, very specific. And that's why these spectra, when they're pure, are category A data for Swig drug. So if we take a quick look again at the cocaine and scopolamine peaks, we see the largest peak is, in fact, the fragment at 82, and there's a bunch of fragments there. But this makes sense now because we're operating at 70 electron volts, and we are, in fact, breaking a bunch of bonds. We do get a little bit of the molecular ion at 303 for each of them, but we get lots of useful fragments. So let's take a look at the parameters here of our actual mass spectrometer. First of all, you can see that we definitely have the vacuum. That's not accurate. We don't go down to 10 to the minus 7 torr. But you can see you can, if you want, you can change the electron energy from 70 electron volts to whatever you want. Don't do this. Nobody really does this. You get terrible signal, but it's an easy parameter change. But we are all going to agree the libraries are set to 70 electron volts. There's the repeller voltage, and you can change the temperature and things. So these are all different parameters for that EI chamber and then further down. Now I want to show you something else here. We saw that for LCMS with electrospray, you could get kind of an APCI as an accessory, and it comes with it most of the time. Same thing with CI. This button is for CI gas, and you can see here there's options in the software. We can say, oh, you know what, turn the CI gas on over here. So it's if you have the accessory, and here we can say, oh, we're going to operate EI in positive mode, CI in positive mode, or CI in negative mode. So if you have the accessory, switching from EI to CI is pretty easy in GCMS. So let's take a look at this chamber again. In chemical ionization, you're going to intentionally leak reagent gas, what's called reagent gas, into this ion source. So let's look at methane. Methane is a really common reagent gas. What's going to happen is if you flood that chamber, it's not actually flooded, but it's essentially you've sucked the air out for a vacuum and you leak back in a little bit of methane. But if you have that in the ion beam, you're going to end up with a cascade of reactions. And these reactions tend to end with a CH5 plus ion, which is crazy. That thing is crazy. You'd get a big F in organic if you wrote CH5. But you can end up with a CH5, and that's going to be really ready to get rid of an H+. So when it collides with your molecule, so you got a bunch of this methane floating around in there and a little bit of your stuff, but when that CH5 collides with your molecule, it's going to transfer the proton. And this is going to be a very efficient method for protonation. It doesn't have to be methane. It can also be isobutane is quite common, and this is gentler than EI. But CH5 still has a lot of energy, so it still does have a bit of a kick to it when it transfers that proton. So if we look at an example here, we look at the ionization of butyl methacrylate, which is 142 Daltons. If we do a 70 electron volt EI source, we don't get molecular ion for this guy. There's no 142 peak. It's too EI, it's too rough. This guy fragments too easily. We get all fragments, which if you don't know what you're looking for, it can be a little bit frustrating, especially if it's something new. Now, if we do CI with methane, you can see, look at that. We get a little bit less fragmentation, and we do get a protonated molecule. We get something that is representative of the molecular weight. If we use isobutane, that turns out to be even gentler for this butyl methacrylate, and we get a very nice protonated molecule peak. So this is a nice way to get molecular information out of GCMS. It's also pretty popular with explosives and forensics, actually negative mode CI, because explosives, their whole point is to fall apart. Their bonds fall apart really easily, so they fragment a lot in EI sources. This is TNT, and its fragmentation is not too bad, but you can see the big peak you get there is 210. That's the loss of the OH. But if you do CI with isobutane and look in negative mode, you do in fact get the M-H peak. That's representative of the TNT. So this can be gentle. It can also be very sensitive. So negative ionization CI can be popular with explosives. All right. So we've gone through some introduction stuff, ESI and APCI, EI and CI. Let's get into some really hard ionization sources. We're going to talk about ICP, and then we're going to have a discussion about isotopes and some information we get from isotopes. So ICP is an extremely hard source. It's going to destroy all the bonds and everything and strip it down to atomic ions. Let's take a look at an ICP torch. This one isn't for mass spectrometry, but it's a really cool looking, powerful torch. So that torch wasn't for mass spectrometry, but there's an ICP torch. This is an animation where you take, and you see you take nebulized sample. It's not ionized yet, but you spray nebulized sample into the torch, and it just destroys it and turns it into these atomic ions. So sample in from the nebulizer, and then atomic ions in the mass analyzer. And these torches really can be as hot as the sun. They can get really, really hot. We actually have one in the lab. They have to have welding glass there. You can't look at it or it'll blind you, but it's actually not that hard to get them. You can pour energy in them, so it's not that hard to make them really, really high energy. These have a lot of uses in trace evidence. When you see them in forensics, ICP has been used for gunshot residue to determine the presence of gunshot residue. Glass inks, tape, those are all real important in trace evidence. And then it's going to be particularly important in nuclear forensics, where you're doing compliance or you're trying to determine if people are making illicit radiological or nuclear weapons. So here's an example of an ICP mass spectrum, and this is from your book. And you can see we're just getting peaks for elements. We're just getting elemental information, regardless of the form it went in. That iron peak right there, I don't know if that was iron nitrate or iron hydride. I don't know what that was because it's ripped apart into elemental iron. But notice the isotopes. In mass spectrometers, we see isotopes. So you get these mass spectra that are just the peaks for the elemental composition. Now, the truth is you see a carbon peak there, but ICP is not really good. We're not going to use ICP very often to look at carbon, nitrogen, oxygen for really small things. ICP really does best for things that are sodium atoms or larger. Mass spectrometry sees isotopes. So this is where the periodic table is going to betray us a little bit. because you can get an idea of what peaks you expect to see looking at the periodic table, usually when you're talking about organic compounds. So let's consider cocaine. All right, I'm going to do, this is in Qual Browser, it'll do simulations of spectra for you. So cocaine's molecular formula is C17H21NO4. I'm going to say C17H22NO4. I'm going to do that to figure out what peak I might see for an electrospray ionization mass spectrum. I want you to think about, why did I put in H22 for what peak I might see? Why didn't I put in H21? Cocaine is C17H21NO4. I put in C17H22NO4. Think about why I might have done that. So here's the simulation. And you can see I get this peak at 304 as I would expect. And I'll show you the real mass spectrum in a second. You also actually see this. There's a little peak at 305, and there's a little peak at 306, and there's actually a teeny tiny peak at 307 right there. This guy definitely shows up, and this guy also shows up. And if we look at the real mass spectra, then we will see that as well. So if we look here at that LCMS data I keep referring to, this was electrospray ionization. If we zoom in there, you absolutely see what we saw in that theoretical spectrum. You see the main peak at 304, but you see a peak at 305 and 306. And those are primarily due to the carbon-13 isotope. We are seeing the presence of the carbon-13 isotope in some of the ions, and that pushes the mass over 1. Okay, this is because of the isotopes of carbon. All right, now you can, so if I just say, show me the theoretical mass spectrum just for carbon, all right? Here's carbon at 12.00. Carbon is by definition 12.00. That is its exact mass by definition, the IUPAC. But look at this, 13. There's a carbon-13 peak because carbon has a carbon-13 isotope. So if we look up carbon, and Wikipedia has pretty good, you need to know the isotope distributions. Wikipedia is pretty good about that. So if we go to, where is that? Down here. The main isotopes of carbon. We see that carbon is about 98.9% carbon-12, but there is 1.1% of carbon as carbon-13. So we see that in the mass spectrum. When we look at the mass spectrum, we see that there's this big guy right here, and then about 1% of that peak is this. And we can actually very specifically look at the ratio of this 12 to 13. We're going to do that with the next ion source we look at. We can very specifically look at the ratio of this 12 to 13 and get some good information from that if we use the right kind of mass spectrometer. So that's for carbon, but in ICP-MS you can't really look at carbon. It's too small. But the thing is, for something like hydrogen, it does have isotope peaks, but they're really tiny. Same thing with nitrogen. Nitrogen has an isotope peak. Here's 14. So here's nitrogen 15. It's really tiny. Oxygen has an isotope peak. There's 16. There's a teeny tiny one at 17, 18, and a teeny tiny one at 17. Carbon has somewhat of a significant isotope peak. But when you're doing ICP and you start looking at metals and things, the isotope peaks are significant. Let's look at lead. Let's simulate the spectrum for lead. Look at that. This is just for lead. There's this 208, 207, 206, and a little 204 peak. So if we look on the periodic table where we're just like, okay, I expect to see lead, then we would say, okay, the molar mass of lead is, or the atomic mass of lead is 207.2. It's 207.2. So I'm going to get a peak on the mass spectrum at 207.2. That's where my lead peak is. No, there's not even a peak at 207.2. You can't really have a peak at 0.2. You have to have pretty close to integer peaks. So remember, we worked on this when we worked on, well, first let's look at the lead isotope ratios. So we have 24% of, about 24% of lead is lead 206. About 22% of lead is 207. So those two are about equal. So we expect a peak at 206 and a peak at 207. They're about equal because they're about equal percents. And then at 208, we have an isotope peak that is 52%, which is about double these guys. So 52% is about double 24 and 22. So we expect to have two peaks that are about the same at 206 and 207, and then a peak that's about twice as high as those two at 208. And that is, in fact, what we see. Two peaks that are about the same size. This one's a little bit smaller. And then a peak that is about double intensity of those two at 208. So these are those isotope peaks. And we dealt with this. You did this in general chemistry. I know those are famous words that you do not want to hear, notorious words. But we did this again in the review problem set with chlorine. This is where that problem comes to life. Chlorine is about 24% chlorine 37, 76% chlorine 35. So there's about 3 times as much. If we take 25 and if we take 24 and multiply it by 3, we about get 76. So there's about 3 times as much chlorine 35 as there is chlorine 37. So if we look at a chlorine isotope simulation, sure enough, we have a peak here that's about 3 times as big as this peak at 37. So that is to say, most of the time with organic compounds, you don't have to worry a whole ton about isotope peaks. Now, we are going to, the small discrepancies in isotope peaks are going to be useful for us in isotope ratio mass spectrometry, which is going to be done with thermal ionization. But when you start looking at metals and things, so most metals have wacky, here's silver. So if we look up silver on the periodic table, if we look for the atomic weight of silver, oh, it's 107.8. But look at that. There's a peak at 107, and there's a peak at 109. There's no 107.8 peak. But they're weighted averages. So the periodic table is going to betray you here. Do not, when you start messing with metals, or really when you start looking at things that aren't carbon, hydrogen, nitrogen, or oxygen, you must pay attention to isotopes. Mass spectrometers see isotopes. That was, in fact, their very first use was pretty quickly after J.J. Thomson and his graduate student Aston developed a mass spectrometer. J.J. Thomson was a physicist and just used it to determine the mass and charge of the electron. Aston said, I think we could use this for analytical purposes. And he actually discovered isotopes because of the mass spectrometer. And then pretty quickly went on to help out with the Manhattan Project to develop the nuclear bomb in World War II, looking at uranium ratios. So if we look at uranium, we see that there's uranium-235 and 238, but uranium's not so bad. So all these metals are, mercury is wild. Look at this. Mercury has this isotope distribution, but yet if you look up mercury on the periodic table, it's just going to give you one mass because it's the weighted average of isotopes. So we'd say, oh, look, mercury's standard atomic weight is 200.5. But then when you actually look at the isotopes, 200.5 is the weighted average of all of these. So when you start doing things like ICP, definitely with thermal ionization, when you start doing work with metals and things that aren't just CHNO, you really have to pay attention to the isotopes because mass spectrometers see isotopes. And this is actually quite powerful. You can use ICP to look at isotope distributions. ICP, is, as we said, is going to be used thoroughly in nuclear forensics because you can verify, you can look at uranium ratios. Uranium is not supposed to be, let's look at uranium again. Uranium is naturally supposed to have this 235-238 ratio, but if you are enriching it for use in weapons, then they intentionally enrichment means they increase the amount of the 235 isotope relative to the 238 isotope, because 235 is more fissile. So uranium 235 is going to be enriched in weapons and things. So for nuclear forensics, they'll go in and get a swab of something. ICP-MS is so sensitive that they can just look at tiny amounts on a swab, dissolve whatever inorganics are on the swab, and then nebulize it into the ICP torch. And if this 235 ratio is big, isotope peak is bigger than it's supposed to be relative to the 238, then whoever that foreign power is enriching uranium. So this is commonly used for by the nuclear forensics community to determine if state actors are illicitly enriching uranium when they're not supposed to be. So we have to pay attention to isotopes, but the truth is we need to have more of that in general chemistry anyway, and the periodic table has been officially changed. The IUPAC decide that atomic weights have to be changed, particularly for some elements. They're starting with some elements, they're going to phase other ends, because atomic weights are weighted averages of all the isotopes for a given compound. So one of the quotes from this particular article, your chemistry teacher probably told you atomic weights are constants of nature, but nothing could be further from the truth. Atomic weights vary depending on where you are on Earth, because the isotopic composition, those percent isotopes, vary depending where you are on Earth, and whether you're in the atmosphere or in the ocean or on the land, and then even then whether in the United States or Europe, and even then whether you're talking about vegetables or other things. So the IUPAC is now going to list on the periodic table. They've started with bromine and magnesium. The official periodic table now doesn't say 79.904 for bromine. It now says 79.901, 79.907, meaning the atomic weight is between those two things. And that's because the relative percent of bromine 79 and bromine 81 varies. So the weighted average varies. Okay, so there's an interactive version of this periodic table that shows the elements and isotopes at isotopesmatter.org. The periodic table of the future is probably not going to look entirely like this with the bar graphs, but what they were saying is if we click on bromine, so if we click on any of these elements, like now we go to silver. We looked at mass spectrum for silver before. If you look at the periodic table, they just give, as you guys probably saw it, they just say, 107.8682. That's not very informative. So they give you the specific isotopes and their ratios here. That pie chart probably is not going to go in the new periodic table, but what is probably going to go in what is already official in the periodic table is, instead of just saying 79.904 for bromine, they're going to put this down here to indicate that atomic mass can actually range from 79.901 to 79.907, because these percentages can shift slightly depending on where you are on Earth. So bromine is not super important to us in forensics, but I'm just using it to illustrate the point here. Here's an example of, this is some environmental work, and what they are doing, and this is going to be really common for a lot of different elements in their isotopes, is you're going to look at how did the relative amounts of bromine 79 and bromine 81 vary. And you can see they vary depending on whether you're in groundwater or brine or this sedimentary formation. What this means is you can take a sample and break it into its elements, and then if you can look at its relative isotopic composition, in this case, the ratio of bromine 79 to bromine 81, that can potentially tell you where that stuff came from, or give you some idea of where that stuff came from. That is powerful and has been incorporated into forensics, but how useful it is in terms of evidentiary value is certainly still up for debate, but it is being used in forensics. So when you look at these minor variations in isotopes, when you look at isotopes ratios, you have to do it in these clean rooms and be very, very careful with a very high level of precision. So you use this really, it's very, very careful, very sensitive work. But you can see noticeable differences in these isotope ratios. So this is an example of a lab in Göttingen, and they are doing isotope ratio measurements. You can use an ICP to do this. You can see this particular instrument. There's the torch. This is an ICP, but there are other methods you can use as well. Another alternative method that's going to be pretty popular for ionization when you're trying to look at isotope ratios. So like I said, you can use ICP. But another possibility is a pretty old method called thermal ionization. So it's just called thermal ionization. A lot of times they'll call it thermal ionization mass spectrometry, or TIMS. And what you're going to do in thermal ionization is you're going to prepare your sample. You have to get it down to a solution. So if it's a rock or something and you're trying to look at the isotopic ratios, you have to dissolve it. There's a lot of sample prep involved, and a lot of times you have to be very, very careful in those clean rooms and things like we saw. You're going to get it into solution, and then you are going to put it onto a filament. This is a lot like what we talked about before with EI, where you had a filament. But we've been able for a long time, it's pretty easy to take a strip of metal and put current through it and heat it up. But here's an example of a rhenium filament. This is for a particular type of TIMS called total evaporation TIMS, but that's okay. You put the solvent on the filament, and then you heat the filament under vacuum to very high temperatures. You can go to 1,000 or 2,000 degrees, and this is going to cause the evaporation of the sample as atomic ions, just basically exposing it to very, very high temperatures, hence the term thermal ionization. So this is kind of an alternative to ICP when you're looking specifically at isotope ratios. It's a bit of a specialized application, but it's very, very popular in nuclear forensics. It is the go-to method for looking at plutonium, uranium, and thorium in nuclear forensics. It's an extremely important method for that field. ICP, though, is pretty generalized. It's very powerful. You can see lots and lots of elements. And in general, if you just want to know what is this stuff and you have no idea and you want the elemental composition, ICP-MS is going to be your answer. If you know what you're looking at, you're specifically looking for isotope ratios, and you're looking at larger atomic elements, lanthanides, actinides in particular, thermal ionization can sometimes give you a little bit more precision. So this is another researcher at that lab we were looking at in Germany, the isotope ratio lab, and she is doing this outside of vacuum. This is actually a preparative step for her, but it's the same idea if she did it under vacuum. You can see she put the solvent on the filament, let it dry up. Now she's going to run current through that filament, and you're going to see it glow red hot. And she's doing this as a preparative step again. But if she were in vacuum doing this step, then that temperature would get really high, and you get a good number of ions off of that. So like I said, this is going to be used in things like, here's an example where they did some determination of the age of plutonium materials by thermal ionization. So they're going to get this kind of data. So they have uranium-234, 235, 236, 238 listed, plutonium-239, 240, 241, 242 listed, and they're going to get the percentages. Here they have the percentages for all these different samples. And based on this distribution of isotopes, they can get a lot of information about that sample. In this case, it's how old is the plutonium, because, plutonium has to be produced. It's not a naturally occurring element, so it's produced and then it decays. But also, this can tell them a lot about what this material may have been used for, and by aging it, they can tell when it was produced. So if someone is saying, yeah, we have this plutonium, but we made it a really long time ago. We made it before we signed that treaty that said we wouldn't make plutonium anymore, or we inherited this from someone else. We didn't make this recently. Well, when you do isotope ratio mass spectrometry, you can tell when it was made, and you can get a lot of information about that sample from this. That information is the backbone for what's called the IAEA, the International Atomic Energy Agency, and they're an international agency that does a lot of nuclear forensics, and countries will often agree to have them go in to see if they are violating sanctions or treaties or whatever for not producing nuclear materials. So just this month, the IAEA analyzed some samples, and isotope ratio is going to be a huge part of that data in North Korea, and found that they are in fact enriching uranium at that facility. So that would be a good indicator that they are in fact continuing work into nuclear weapons. So that kind of information, when you see that in the news, like they're continuing to make nuclear weapons or they stop making nuclear weapons, a lot of the basis of that information is mass spectrometry, ICP or thermal ionization mass spectrometry, and looking at the ratios of uranium and plutonium and other important lanthanide and actinide elements. So that's what we call nuclear forensics. So we talked about looking at the ratio of isotopes for different elements for big things. We looked at lead and mercury and all these other things, and then uranium and plutonium, we talked about those. But it can be really, really useful to look at the isotope ratios for carbon, hydrogen, nitrogen, oxygen. So you can get some information about organics. Obviously, there's carbon 12, carbon 13, oxygen 16, oxygen 18. Those guys, the relative isotopes for these different elements. Now, there's not as much of the other isotopes, but we can measure these really, really accurately, and we can get good information about them. We have to approach it a little bit differently in terms of ionization, because they're organic compounds. They don't do well in ICP. They don't do great necessarily with the same kind of thermal ionization we just talked about. But it's important information. It turns out that this on the x-axis there is the relative carbon-13 ratio, and we'll talk about that more in just a minute. But you can see that if you are eating food in the United States, then the carbon that you incorporate because of what you are eating has less carbon-13 in it than if you were in Europe. So you can actually pull beard hairs is one thing they've done commonly, or pull people's hairs, and you can just look at the relative amount of carbon-12 or carbon-13 in their hair, and that hair was produced based on the food that they ate, and you can tell with reasonable certainty whether they were eating food in the US or eating food in Europe. So obviously there's a lot of promise there to be able to source things, to look at isotope ratios and say, where did this stuff come from? A lot of that promise has been realized, and you can use this data to try and figure out where things came from. It has not reached the level, it hasn't crossed the bar where you can use it reliably in court and say, this definitely came from this. But it is actively being used for intelligence purposes to tell people where things came from. Now, if you have organic compounds, carbon, hydrogen, nitrogen, oxygen, and you want to break them down into their constituent elements, you don't need a torch as hot as the sun. You don't need an ICP torch. You don't need a thermal ionization filament that's going to 2,000 degrees. You can just burn them up, all right? You can just combust them. And so you'll see here in the instrument, you can take the sample in kind of a foil capsule. You can also do this with GC or LC. It's a little bit more difficult. But you put them into what's called a combustion tube, and it's just going to tear that CHNO, that organic compound, down into gases like N2, NOx. CO2 is a big one. Most of the carbon is, because remember, when you combust carbon, once again, I am saying, remember in general chemistry, but the combustion reaction is carbonaceous compound plus O2 goes to CO2 and water. Well, you do that, and all the carbon is converted to CO2. You haven't changed the isotope ratio. You haven't changed carbon-12 to carbon-13. That's undisturbed, so the chemical form doesn't really matter, but CO2 is a lot easier to deal with. So you put whatever sample in this chamber, you burn it up, and then it comes out of this chamber as CO2, and then you are going to put it through a mass spectrometer and determine the relative ratios of carbon-12 and carbon-13. So for each element you look at, you have to choose a standard. You have to choose some material and say, okay, this is the relative isotope for that element that we're going to look at. We're going to compare everything to that. For carbon, the carbon-12, carbon-13 ratio, the standard carbon-12, carbon-13 ratio is from what's called the PD region. This is for the whole world uses this, or they used to use it. They actually kind of ran out. But it's this PD river between North and South Carolina. It straddles both of them there. And the formation along the side is called the PD formation. And in this PD formation, there are fossils called belemnites. So this PD formation has a lot of these fossils called belemnites. Now this may all sound esoteric, but strange as it seems, it turns out that the belemnites from this PD region have the highest percent of carbon-13 of anything that we have discovered on Earth. They are the most enriched in carbon-13 of anything on Earth. So they are the standard, the PDB, the PD Valley belemnite, PD belemites. They are the standard. You grind up these belemites, you convert them to CO2, and you're going to get more carbon-13 enrichment than anything else on the planet. So if you want to do carbon isotope ratios, you get a PDB standard, and you say, okay, my thing has a carbon-12, carbon-13 ratio of this. How different is that to the PDB? And we call that the carbon shift, the shift in carbon-13 ratio. And it's always going to be negative because compared to the PDB, the PD belemite, everything else on Earth has less carbon-13 in it. That's the official carbon-13 standard. It turns out they don't have any more PD belemite left, so they've had to make an artificial standard. But everything else has a standard as well. Nitrogen has a standard, oxygen has a standard, hydrogen has a standard, etc., etc. So here's a table of delta carbon-13 shifts, and you see they're all negative because this is the carbon-12, carbon-13 ratio relative to PDB. But PDB is the biggest one you can have, so they're all negative. The shifts are all going to be negative. But the shifts can be distinguished from each other. If you're very, very careful and you go out to a lot of decimal places with your carbon-12, carbon-13 ratio, you can find significant differences between these things. So even if you look at the difference, if we just look at the United States, there's differences between if you eat meat, the carbon-12, carbon-13 ratio, versus if you were eating nuts, versus if you were eating fruits. And then if you're eating things in the United States versus Japan versus Europe, then the carbon-12, carbon-13 ratio shifts. So in this experiment, these guys like to use beard hair a lot because it grows fast. Head hair, you'd sort of have to shave and pick stuff close to the root. But you can actually start off, you can be someone who lives in the United States, but you go to Japan for a conference. And then while you're in Japan, you're only going to eat food from Japan. That was, domestic food, of course. And then you're going to let your beard grow a little bit, shave off those hairs, and you actually see a shift in the carbon-12, carbon-13 ratio in your hair. Your whole body has shifted. The hair is just the easiest thing to sample. And certainly if you go to Europe and you're from the United States, you can tell after a week or so of being there, your body has incorporated a lot of that food and hair grows pretty fast. You will be able to see the carbon-12, carbon-13 shift in your body. Your ratios will have shifted as you uptake. Your source of carbon becomes that European carbon. So the power here is being able to source things and getting information about where did this come from, regardless of its chemical identity or its molecular structure. Where did the carbon, hydrogen, nitrogen, oxygen that makes this thing up, where did it come from? What area has carbon-12, carbon-13 ratios or nitrogen isotopic ratios or oxygen isotopic ratios that are consistent with what I'm observing in this sample? And that kind of measurement is being actively done at the DEA. The DEA does isotope ratio measurements, and there's data. There's established data. So this is cocaine, and they combine the information from the carbon-12, carbon-13 ratios and nitrogen-15, nitrogen-14 ratios. But they can take cocaine, doesn't matter if it's powder cocaine or what form it's in, it doesn't matter. If it came from a leaf in Central South America, then the leaf was consistent, and then everything that comes from it, the cocaine and everything else that comes from it, is consistent with the carbon and nitrogen ratios from that region. So you can take powder cocaine or crack, and you can combust it into CO2, and then look at the isotope ratios. If you're very, very careful like we saw, and you use a very precise sample prep and a very precise mass spectrometer, and then based on the database they have, you can tell where that cocaine came from, where in Colombia, Belize, Bolivia, where that cocaine came from based on these databases. So that is powerful information for intelligence. And this has also been extrapolated to explosives, using isotope ratios for explosives. And these are actively being done for intelligence purposes. Okay, so we've gone over some background. We did ESI, APCI, EICI. We've done ICP. We looked at elemental and atomic ions, and we talked about isotope ratios. Let's finish up talking about ambient ionization. So I want to show you that one of the first reports of ambient ionization to tell you how cool it is. So this is an example where this gentleman deliberately wore this tie, these clothes. He was from the Boston area, and somewhere around that area, a building was being demolished, so explosives were going to be used. So he went to view the demolition. He stood at the periphery, at the sort of roped off area, the closest the public was allowed to get. So he was, far away from the demolition, but he made sure to wear that tie. And then he came into the lab, and having done all that sample prep work that we think about we would start to think, okay, if I want to try and find explosives on this tie, what am I going to do? Okay, they're explosives. I'm going to take this tie, I'm going to rinse it with water, and then I'm going to rinse it with acetone, and then I'm going to dry those up, and then it's going to be gross because it's a piece of clothes. Acetone's going to pull a bunch of garbage off of it. We'd be thinking about all this sample prep work that we had to do. But the thing that was so exciting when they reported this is for ambient ionization, for this particular method, it's called DART. All he had to do was take his tie and put it in the gap between the ion source and the mass spectrometer, and with no sample prep and no chromatography, and directly off the tie, they were able to see the nitroglycerin peak for the explosives used in the demolition. So this is the promise of ambient ionization. You guys can appreciate this now that you've done a bunch of sample prep and a bunch of other work. You can really appreciate the idea that you can just skip all that. Mass spectrometry and all those other things take all the sample prep. Wouldn't it be wonderful to just skip that and just shove stuff into a little gap and immediately get mass spectra? That's really the promise of ambient ionization. So what we're going to do in ambient ionization, you can see that in that schematic there, is the ion source is going to be outside the instrument, obviously at ambient pressure, hence ambient ionization. And you're going to put the sample between the ion source and the instrument. You're going to put the sample in a gap between the ion source and the instrument, and you're going to desorb gases from the sample, and they should leave the sample as gas phase ions and then go into the mass spectrometer where they can be analyzed. So the first ambient ionization source we'll talk about will be DART, and that is the source we were just looking at. So I really like DART, and it's the ambient ionization technique that's been most widely adopted by the forensic science community, particularly forensic chemistry. There are several forensic chemistry labs now that use this guy for drugs routinely in their casework. I really like DART. I do collaborations with the company that sells the DART source. But DART is a terrible name. It's a good commercial name, but direct analysis in real time, you may hopefully have noticed that the rest of these names actually have something to do with the science. DART has nothing to do with the science, so I will apologize that you have to memorize the term DART when it has nothing to do with the science. You could call any ambient ionization technique direct analysis in real time. But anyhow, it is a very good technique, and it's closest to APCI. Remember, in APCI, you generated a corona discharge, and that ionized molecules in the air around you, including nitrogen, oxygen, and water, and you ended up with a lot of hydronium ion, and then that tended to do a proton transfer with your sample. The H3O plus could donate to your sample. One thing with corona discharge, though, is if the ionized nitrogen or oxygen, which tends to be radicals, if they collide with your sample of interest before the hydronium ion does, they can impart a lot more energy and result in a lot more fragmentation. DART takes a little bit different approach. You see that there is that high voltage needle. That is a corona discharge. That's a needle. You apply high voltage, you get a corona discharge. But that needle is not in air. The gas flow, the green tube there, the gas is helium. You're flowing helium through into the corona discharge region. Flashback once again to our general chemistry periodic table trends with ionization energy or ionization potential, and ask yourself, who has the highest ionization potential of anyone in the periodic table? Well, the answer is helium. The answer is helium. So helium has such a high ionization potential that even though you're pumping energy into it with that corona discharge, that high voltage needle, it does not ionize. It takes on energy and goes to an excited state, but it does not ionize. We call this excited helium, but it's excited but not ionized. We call it metastable helium. So helium metastables come out of that high voltage needle, and then you'll see there's a heater there, and that heats up the helium gas that's going to come out the front of the gun there. And the reason that we need to heat up the helium gas is we're going to have a good mechanism for ionizing things, but remember, if you're going to go to the mass spectrometer, the big rule is you got to be an ion and you got to be a gas. So we need to make things gases. So we just use heat. We heat up the helium to 200, between 150 and sometimes up to 300 degrees. And so we're actually going to just thermally desorb or kind of evaporate things off the surface with the heated helium. So that's how we get it to be a gas, is with heat. But the ionization mechanism is through these excited helium metastables. Now, next to the heater, you see the grid voltage. That grid is actually there to make sure if there was any air, residual air ionized in the corona discharge, that grid has a negative charge on it, so positive ions stick on it. The helium metastables don't have charge. They don't even notice the grid. So they come shooting out the front of the gun, the helium metastables do. They crash into the air, and then, similar to APCI, they're going to generate a lot of hydronium ion that can protonate our sample. They are also going to generate some nitrogen, oxygen ions and radicals that can crash into our sample. But for the most part, these helium metastables leave the gun into that open air sample region, the gap. They crash into the air, and mostly what the reaction cascade is going to generate is hydronium ion, H3O+, and that's going to do proton transfer to your sample after it's heated so much that it leaves the surface or evaporates into the gas phase. It then gets ionized primarily through that proton transfer and then shoots right into the mass spectrometer. So here's an example of one of my students, and she's just straight holding a marijuana leaf in that gap, and boom, you get the THC. Here's another example. This is a way that drug labs run this. You can see the mass spectrometer is just running in time. She's got cocaine residue on the tip of that capillary. She puts it in the gap, and she gets, boom, that 304 peak for cocaine. This is how most crime labs run it. You can ignore this fragmentation part for right now. This is a good preview of the next video when we talk about MSMS fragmentation. But you saw she had a little bit of cocaine residue on that capillary on the closed end. She shoved it into the inlet, and she got the peak. Now, that looks like a chromatogram. It is not. There's no chromatography going on here, but it is the signal over time. The term people usually use for that is the chronogram. It's just a signal versus time. You can see when she shoved it in and when she took it out because the peak popped up and then it popped back. But it's not chromatography. It's just signal over time. Okay, the next ambient ionization source we're going to talk about is desorption electrospray ionization, or DESI. This guy also kind of plugs into the front of the ionization source, and the best way to talk about this is this wonderful animation. So here, this is going to be a lot like electrospray. We're going to have solvent and high voltage and a spray head, but we're going to use this gas inlet, and we're going to use a lot of gas. It's kind of like a pressure washer, and there's no sample. It's not like electrospray where there's sample coming through the electrospray needle. We are just going to spray solvent ions. The spray head is, you're going to crank up the gas, so like I said, it's like a pressure washer, and the stuff bounces off the surface. Here they're using a pill into the inlet of the mass spectrometer, but it's going to blow particles in the mass spectrometer, but also the solvent that it's blowing from the electrospray is ionized solvent. So whatever methanol or acetonitrile or water, usually it's going to be a mixture of methanol and water, they're going to be ionized from the electrospray process, but they're still droplets, and they can bounce at the surface, but when they hit the surface and before they leave and bounce off, they desorb, or they soak up some of the sample. They dissolve a little bit of the sample, and then those droplets get pushed in the mass spectrometer, and in those droplets, they're also transferring protons. We are spraying ionized solvent at the sample. So here's another example of you just put the stuff in the gap, and you get mass spectral peaks, and they're sort of scanning across two different tablets, and you see the peaks go away when you're not scanning across the surface. The last ambient ionization method that I want to talk to you about is called paper spray. The DEA has used DESI. A bunch of labs have used DART. Paper spray, the Dutch Forensics Laboratory, the Dutch National Forensics Laboratory, the Netherlands Forensics Institute, has tried paper spray, and they've gotten very close. But this method holds a lot of promise, particularly in toxicology and in swabs for trace residue. So this is looking toward the future. I think it's going to be important in the future. And basically, this is an electrospray method, but it's electrospray off of a piece of paper. It's pretty wild that you can get away with this. So what you're seeing here is kind of a fancy piece of filter paper that's been cut to a tip, and they put a droplet of blood. That red spot is right there is supposed to be blood. Now, you know, normally you have to do a lot of sample prep, a lot of work to get blood ready for analysis. But you can get some decent data with paper spray by taking the blood, dropping it on this paper, and then what they're going to do is they're going to deposit some solvent at the base of the paper, and that solvent is going to wick up the paper. And it's going to extract some of the blood components and bring that up towards the front there. Now, you don't have to have this big fancy instrument. This is an instrument they propose, but that's a high voltage cable they've got there. And what they're going to do is they're going to make high voltage contact with the paper, and it turns out you can electrospray directly from the paper, which is pretty remarkable. So they're electrospraying directly from this filter paper, and that's going to do an electrospray mechanism where you produce gas phase ions off the stuff that was in the blood. You lose a little bit of sensitivity, but it's pretty remarkable how decent the sensitivity is for how little sample prep there is. You're just dropping blood onto a filter paper. So let's look at an actual paper spray experiment. This guy, you can just take regular filter paper. He's taking filter paper, he's cut it into this shape so that he has a tip. He has a nice sharp point there, and that's going to be a spray point. And then he's just barely swabbing. I think that's a perfume sample on a slide. He's swabbing that, and then he has a simple setup to apply high voltage to the paper on the inlet of his mass spectrometer. So he puts that clip there, and he can apply 5,000 volts to that clip. So then inserts that in the source region so he can apply the voltage and be nice and safe. And then you can see in the camera he's got that tip right next to the inlet. He puts on a little bit of solvent there, and that's going to wick the sample, and then he applies the voltage. And in real life, you don't usually get to see the spray. Sorry, he's making the droplets. You don't usually get to see the spray, but he is currently electrospraying into the instrument, and he gets the peaks expected in real time directly from that paper. So he just swabbed that paper on there. And there's been some really nice experiments in Chris Mulligan's lab, funded by the National Institutes of Justice, where they're very interested, and he's shown that it's quite feasible. You can take pieces of filter paper and swab things like door handles with them, and then cut them into a triangle and put them in a paper spray source, and you can see if there was just trace amounts of cocaine on the door handle. This has potential for explosives or anything. You just sort of cruise in, swab the surface, and with exquisite sensitivity, you can see what was on that surface. So the paper spray has a lot of promise in toxicology, and the Netherlands Forensics Institute got pretty close to implementing it in toxicology, but they didn't meet the detection limit they needed for THC. They met the detection limit for most of the other drugs. And it also has uses for potentially defense forensics, military applications, and then conventional forensics, where you're swabbing surfaces, and then you turn the swab itself into an ion source with good sensitivity. So we covered a lot of territory. We started off looking a little bit at mass spectra, some characteristics of mass spectra. We'll look some more of that in the next video. Then we looked at block diagrams, components, talked about vacuum, some general characteristics of ion sources. Remember, we primarily grouped them by what kinds of ions do they make. A shorthand way for that, to say that, is how hard is the ion source. We looked at ESI and APCI, which are going to be the primary methods for LCMS. They work well with liquids. We also looked at EI and CI, which work well for gas chromatography mass spectrometry, GCMS, because they work with gases. I'm going to pause here for a moment for a public service announcements. Look at ESI and DI. You might just write them out. You might just write them out instead of saying ESI and EI. It's really common for students on exams to tell me, I'm going to run LCMS with EI. No, you're not. EI is for gases. You have to be a gas before you work in EI. You probably meant ESI. The acronyms are very close. Or if you said to me, I'm going to do a GCMS, I'm going to use an ESI source. No, you're not. That is electrospray. It's a spray of solvent. It's not for gases. So if you're worried about confusing those acronyms, just write out electrospray and electron ionization. So we went over ESI and APCI. We went over EI and CI, which is good for gases, so a couple of GCMS. And then we talked about ICP and using isotope ratios for isotope ratio mass spectrometry. We also did thermal ionization as part of that. And then we also said, well, for CHNO, if you're just looking at their isotope ratios, you should combust them. You should burn them up and convert them to CO2 and NOx and H2O and stuff. And then we looked at ambient ionization sources, which allow you to skip all the sample prep and get results immediately. We looked at DART, DESI, and paper spray. And in the next video, we will look at mass analyzers and a little bit about detectors.